Okay. Hello and good morning, everybody. Thank you for joining. My name is Jackie, and I'm joined with my teammates Stephen and David, and our capstone project is the Formlabs SLS powder recovery system. Before we get started, we'd like to share some acknowledgements of people who have helped us along the way. First, we'd like to thank Steve Chomziak and Formlabs for being great mentors throughout the whole time of this project. We'd also like to thank the team at Epic, especially Jeff, Joe, and Bob for the machining and controls portion. We'd also like to thank the Boston Gear Company for donating some gears to our project. And finally, Professors Thornton, Russo, Gutierrez, and Hauser for their mentorship. So we'd like to start with a little agenda to go over what we'll be discussing today. We're going to start with the introduction, move into the problem definition, and talk about the key specifications. And then we'll discuss the subsystem designs and analysis, experimental results, the next steps and recommendations, and finally, we'll have some time for questions at the end. Formlabs is an additive manufacturing company that makes SLS printers for industrial and personal use. SLS stands for Selective Laser Sintering. This machine uses a laser to sinter powdered plastic material into a solid structure based on a 3D model. Our project is focused on optimizing the Formlabs SIFT. The SIFT is a post-processing machine that is used to remove and collect excess powder from the Fuse 1 SLS prints. It also doses fresh and reclaimed powder in specific ratios, dispenses them into a container, and mixes the final volume. Our product is important because we are designing a solution for a faster mixing time and looking to avoid machine maintenance with the dispensing and dosing that often occurs with clogging of powder. Our problem definition is to fill a container with a homogeneous, adjustable ratio mixture of fresh and reclaimed nylon powder, dosed from separate feed containers, considering cycle time, size, cost, and environmental/user safety.
So here's a list of some specific requirements that our client wanted us to accomplish in this project. The first major goal was to expand their current final mixture volume from 5 liters to 20 liters of powder. Next, the mixture ratio had to be controlled. This is a little equation that describes that ratio. For example, one common mix ratio they use is 30% fresh and 70% reclaimed powder. The dimensions of the final product had to be in similar proportions to the existing SIFT1 shown above. The total time it takes to fill the final container with 20 liters of powder had to be 5 minutes or less. It had to plug into a standard 110, 120 volt outlet. To judge the effectiveness of the system, the machine had to run continuously without any clogging issues. And finally, the final volume only had to be visually mixed. Precise homogeneity of the final mixture was not a critical metric for the success of our design. So the first component of our design are the hoppers, which are used to hold the powder. The design of the hoppers turned out to be one of the biggest obstacles that we overcame during the project. A big issue when dealing with powder handling is rat holing and bridging, shown in the picture on the left. To solve these problems, we implemented an agitator in each of the hoppers that is driven by a chain and sprocket system. This way, whenever the system is running, the agitators are breaking up any clogs and keeping the process moving. In regards to the geometry of the hopper itself, we went through multiple iterations to find out what could hold 12 and 18 liters of powder and still have an optimal angle of 20 degrees for powder flow. We also chose polycarbonate for our final material so we could see inside the system as it was running and maintain structural integrity. The next component is the dosing. The dosing mechanism we chose for our system is an auger screw. We printed multiple iterations of the augers using the Fuse 1 and the PA12 nylon powder. Through the different helix profiles and dimensional differences that we tested, all of the augers proved to be an effective and reliable method to dose the powder. The augers are driven by a 200 RPM DC motor, which also drives the agitator through the chain and sprocket system. So for this system, we needed to vary the rate of the augers so they will both dose powder continuously for the same period of time. Therefore, one auger must be adjusted to maintain a smaller mass flow rate that will have both augers run for the same length of time to get the correct mix ratio. The required relationship is shown here. We chose to use this relationship with a pulse width modulation for ease of programming. Pulse width modulation means that one auger is pulsed on and off at various time intervals according to this duty cycle curve, while the other runs continuously. However, we would recommend that an actual system use variable speed motors that can be monitored by the system. Using variable speed motors would lengthen motor life and also be more continuous and reliable. So to continually mix the powders in a homogeneous mixture, 2 paddle wheels are spun at 1,000 RPM using gears as shown. We determine a speed of 1,000 RPM is needed to fling the powder and not just dump the powder forwards. We designed a few iterations of paddle wheels that can be swapped in and out of the system as well. To prevent powder from getting stuck in the paddle wheels, we designed them with a curve in between each blade. We also determined that there were not any significant differences between designs with more or less paddles when they're spinning that fast. The powder is flung and continuously mixed in this process and then falls down into the final collection chamber. The process continues until the scale detects that the bucket is filled with 20 liters of powder.
So here we see the control interface. It has one dial to set the fresh powder percentage, 3 controls buttons, and an e-stop. There are also 5 indicator lights which show the user which system state the machine is in. To begin the mixing process, the run button is pressed. The system will run until completion unless it's paused or reset. The fresh powder percentage is determined by the adjustable knob, and the motors can be seen starting and stopping according to the pulse width modulation duty cycle. The motors can also be stopped using the e-stop button, which cuts power to the mechanical components of the system while still maintaining power to the essential controls. And the process will automatically stop when it has reached a weight of 15 kilograms, which is based on the weight of a full bucket of powder. When this happens, the full bucket indicator light turns on, and the system cannot be prompted out of the idle state until it's been unloaded. So here's a video of the various components of the system in action. During our experiments, we used 2 different types of powder, gray nylon powder, which is used at Formlabs, and powdered sugar. So these powders have similar particle size, density, and other properties, but they're visually different, which is why we chose them. So in our experiments, we considered the powdered sugar to be the fresh powder, and this video demonstrates a typical mixing process that the system would perform. So in this mixing experiment, the machine was set to make a mixture of 30% fresh powder and 70% reclaimed powder. Since the machine is set to 30% fresh powder, the powdered sugar is being dosed slower than the nylon powder with the pulse width modulation control. So inside the mixing chamber, the 2 powders are continuously mixed together, and they're dispensed directly into the collection chamber. Next, we'd like to discuss the analysis of our system and its various components. So first, we'd like to discuss the successes and failures of the hoppers. The motors that we currently have were unable to handle the torque needed to agitate and dose a totally full hopper, so we could only dose smaller amounts of powder in our experiments. On the left, you could see that the nylon powder flows completely from the hopper without any additional agitation as desired. On the right, we demonstrate that there needs to be additional agitation to make the stickier powdered sugar flow out of the system without any bridging or rat holing. So here's another example of bridging and rat holing in the powdered sugar hopper. And to resolve this issue, we had to manually break up the bridging at the bottom of the hopper with a small rod. This additional agitation allows all of the powder to flow out of the system as desired. And in the future, we suggest to add additional agitator closer to the auger or to add a wiper blade on the side of the hopper. But despite all these issues, we were satisfied with the design of our hoppers since we were able to maintain consistent hopper flow from nylon powder that would actually be used at Formlabs. We went through many iterations of hopper design to determine the best way to maintain this reliable hopper flow. While the powdered sugar is a little sticky, the nylon powder flows really easily. The nylon powder flows so well that it leaks out the backside of the augers when they're running, and it also leaks out the mixing chamber even when the system is not turning. So since powder characteristics are so strange and variable, we found that it's essential to try and keep the powder fully enclosed at all times by sealing every interface between different parts. Sadly, this is not something we were able to accomplish with our initial prototype, but in the future, to solve these issues, especially the powder flowing past the auger, we'd suggest to make the auger tube longer or to angle it upwards so the powder can't flow out of the system in the way shown in this video. In order to determine the mass flow rate and the overall cycle time of the system, we measured the mass dispensed by the system and the time needed to dispense that amount of powder at different powder types and different speed ratios. So at the max speed, the nylon powder has a mass flow rate, which is almost double that of the powdered sugar. We believe this happened because the nylon has a slightly higher density than the powdered sugar, and also because the nylon flows much better than the powdered sugar. The powdered sugar packs into the helix of the auger, and it has all the flowability issues that we previously discussed. According to the duty cycle relationship that we calculated, the flow rates at a 70-30 mix should be about 43% of the maximum flow rate. So we believe that the flow rate of the nylon is above this 43% of max just because there is leaking issues. And then for the powdered sugar, we believe that the value is slower than the 43% just because it's so sticky and the pulse width modulation is not the ideal way to decrease the mass flow rate.
In order to test the mixing capabilities of the system, we use powdered sugar to represent fresh powder and PA12 nylon to represent reclaimed powder. We recognize these two powders do not have the exact same flow rates or properties, but for the sake of the powder options we were available to get, this was the best choice since they have similar properties but are visually distinguishable. For the requirements of this project, we were expected to mix the powders and inspect them visually for a homogeneous mixture. As we previously stated in the specifications, our client was not deeply concerned with the analysis of the mixing for the scope of this project. For our experiments, we tested 70-30, 50-50, and 30-70 ratios. Formlabs typically uses the ratio of 30% fresh and 70% reclaimed for their prints. In these experiments, we loaded 1 kilogram of nylon powder into the hopper and loaded the powdered sugar hopper more than the amount needed to complete the mix. The results of the dosing can be seen on the following graph. Since we always loaded in 1 kilogram of nylon powder, which we considered the reclaimed powder in this scenario, the expected amount of mixed powder in the final bucket increased as we increased the fresh powder percentage. These results show that the mixed batches appropriately increase as we expected based on our control system, and the process is repeatable. We believe that the tests that required 70% of the powdered sugar were below the expected curve because the mass flow rate of the powdered sugar was less than the nylon powder. Since our motors are not speed controlled, we were unable to accommodate for this issue and the overall mass was below the expected amount. These images are not the phases of the moon, but in fact the final powder mixtures. Here we can see the results of the mixing experiments. From visually inspecting the batches of different mix ratios, we can see the predicted gradient of the mixtures to be accomplished. The mixture with the highest amount of fresh or powdered sugar is on the left, and the mixture with the highest amount of reclaimed or nylon powder is on the right.
So to evaluate our final prototype based on the goals our client set for us, we were able to complete a majority of them. We were not able to fill a bucket with 20 liters of powder because of the weak motors, leaking, and rat holing that occurred in the hoppers. We were able to control our powder mixture effectively as shown in the mixing test results. The dimensions of our prototype stayed in relative proportion to the existing SIFT-1. Our total mixing process time was only able to be estimated, but even then it was not in our 5 minutes or below time goal. We were able to plug in the entire system with one power cord. Our system met half of the effectiveness criteria since it was continuous while the system was running well in small batches, but it did have issues with clogging and rat holing. And finally, we were easily able to see the final mixed volume in our tests.
Some immediate improvements we would want to make on the system are to upgrade the motors to have a higher torque and have variable speed control. That way we would have more accurate and sustainable dosing. With a motor upgrade and minor leak prevention, our system should be able to achieve the 20-liter 70-30 mix, which was a major goal of ours. We'd also like to sophisticate the controls so that the powder ratio is locked in place when the system is set into the running, and then it is only reset when the system is stopped and reset. We'd also want to add a more sophisticated touchscreen interface for a final prototype. A huge improvement for reliability and safety would be to keep the powder enclosed at all times by adding seals at every part interface. This would require some dry seals on the augers, and that would improve the way that powder is poured in and out of the system. We would also want to improve powder agitation, as previously discussed. We could also do more to optimize many components, such as optimizing the auger screw to have a higher flow rate with lower friction. And finally, we'd want to do more extensive testing to determine the exact feed rates and system times. We'd also want to push the system to its limits and test its robustness. So long-term goals that would fit in this project are to fit the system into the existing SIFT architecture and to have the process connect powder directly back into the fuse.
Thank you for listening to our presentation. It was a pleasure to work on this year-long project. Now, does anybody have any questions?